Hello, it's Ryan. This is our second example using Coulomb's law. It says assume that an electron orbits a proton in uniform circular motion, and so we'd be talking about a common hydrogen atom. It says determine the electron's tangential velocity, ignoring any motion exhibited by the nucleus. And then I note on there that a sub O, which is what I'll label the distance between the electron and the proton in our common hydrogen atom, is defined as something called the Bohr radius. And the Bohr radius is always 0.529 angstrom, and I wrote what 1 angstrom is. We often use a unit in angstroms to measure atomic distances. So we're going to start this out with a picture like always. And in our picture, I'm going to note or remind us what we know about uniform circular motion. Keep in mind anytime something's moving in uniform circular motion, so we'll say recall uniform circular motion. There are some YouTube videos on my channel if you need to check those out to remember some of this stuff. But we need a real center-seeking force, a force toward the center of the circular motion exhibited by the particle, causing that centripetal or center-seeking acceleration that allows the particle to move in uniform circular motion. It's quite a lot to take in. We sum it all up with Newton's second law. The sum of the forces in the centripetal or center-seeking direction is always equal to ma, but Ra is the center-seeking acceleration. We might then simplify this a little because of some derivations you can do. That AC is always, the centripetal acceleration is always the tangential velocity squared over the radius. So this can be written v squared over r, and that v is v tangential, but I don't want to write that and confuse people into thinking that it's actually a tangent function, because it's not. Anyway, this is something we know for uniform circular motion, as long as the force is center-seeking. So going into our picture, we're going to draw a cute little proton. There it is, with an even cuter electron orbiting it. And that electron, we're assuming, will move in uniform circular motion around the proton. That's a little bit more angular, but pretend it's a circle. We know that the distance between the electron and the proton is the Bohr radius. And we know that this electron will have a tangential velocity, a velocity that touches the circle at one point, so it's tangential, like so. We also know that the electric force on that electron due to the proton will be attractive because they're opposite charges, and so the electric force will cause a center-seeking acceleration, which is really why we get the nice uniform circular motion. So this is a decent picture. We could also, just for funsies, show the FBD of our electron. It has an electric force, Fe, on it. That also will cause an acceleration. And those are the only forces we're worried about, so that's what shows up on our FBD. I'm going to choose this direction to be our positive x direction, just so that I don't have to worry about unnecessary negative signs. And so, of course, we could show that the sum of the forces on our electron, which are toward the center of the circle, will be MAC on the electron. Well, the sum of our forces is just Fe, mv squared over r, which r was the Bohr radius, so we could input that. Fe is k, q1, q2 over r squared, mv squared over r. So it looks like if we multiply both sides by r, one of those square r's will go away. I think the question is asking for this tangential velocity here. And so what we're going to do is isolate that with a little bit of algebra. We're going to divide by m and square root. So we get v equals the square root of, we have a k, q1, q2 over, the r is still there. And now the m is moving to the bottom. And so we have mr. All right. So we've got a bit of a solution for us. I'm going to go ahead and substitute the values. That's always our next step. And as you've noticed, I always input the units on all of my numbers. You don't want your numbers to feel naked out there. So we're going to put in the charge. Well, the charge on the proton and the charge on the electron are the same, actually. Q1 equals Q2 equals 1.602 times 10 to the negative 19 coulombs. And remember, for the electric force, I don't really want to put in the negative signs. So we'll have 1.602 times 10 to the negative 19 coulomb, and that's going to be squared, divided by m. The mass of the electron is 9.109 times 10 to the negative 31 kilogram. And we're going to multiply by the Bohr radius, which was 0.529 times 10 to the negative 10 meter. And so you'll definitely want to practice plugging this into your calculator. A lot of students make calculator errors in this class. V is equal to, now V is a velocity, which is in fact a vector. So we want to write this as a vector. I chose it to be in the x direction, so it's not really going to add much to our answer. If you calculate this all out, I think you should get 2.19 times 10 to the 6 meters per second in the x direction. We could write this as 2.19 mega meters per second in the x direction. I like that. Another way you could write, instead of, if you don't want to write in the x direction, if you don't feel comfortable creating a directions for yourself like that, you also could say tangentially, right? Because that's really the direction of the velocity at any time, tangentially. So that would take care of our direction as well. So that's our second example using Coulomb's law. And we really used Coulomb's law and an idea of uniform circular motion from Physics 1. So I'll bet you'll have to remember that as one of your topics from Physics 1 as well. Although I won't ask you to do too much with it, I'm sure. Just remembering this relationship is probably enough. Anyway, good luck. See you in the next example.